Okay. Hi, everybody. This is the webinar on the use of ArangoDB Agency as a fault-tolerant persistent data store. I'm Kaveh, and I hold a PhD in physics. I've been working with ArangoDB now for almost 2 years. And my development work has been involving the agency, the ArangoDB Agency, and core infrastructure in the cluster. All right, let's get started. Yeah, I'm going to give a quick introduction. I would like to explain some of the motivation why we did this, describe problems that in the end of the day, for every software project, are to be solved, and also how we did the solving, and what the consequences of pursuing the consensus the way we did has, in terms of advantages and disadvantages. Okay, so to start off, when you want to run a software in a cluster, size of thousands and thousands of computers, like a database cluster, in our case ArangoDB, you have to have a couple of things as a ground truth that all all servers that are in the cluster agree upon. For example, in our case, this would mean that if you create a collection that is sharded among many computers, then obviously coordinators need to know where to find the different shards of that collection, so that the queries can be accordingly formulated, collected, aggregated, and delivered back. And also, obviously, the DB servers themselves need to somehow find out that they have to do something in the context of creating a collection and index, vice versa. Okay, so the problem that you face in a setup like this is, in reality, you're dealing with real computers and real networks and real people. Computers can be wrongly configured, maybe for just a couple of seconds, and then correctly restarted. Your network hardware, starting with switches over routers, over wrongly configured network interfaces, can show all sorts of undefined behavior. And then, obviously, people are involved, and people make mistakes. The way to solve this kind of problem, that is a global ground truth, is done via things that we call consensus protocols. These, there are lots of publications on consensus protocols. I will touch upon that in a moment. But in the end of the day, even if you have research publications and such, there's always space for getting things wrong. So you're really tough to, in the end of the day, actually make a software work the same way the authors of a theoretical framework or so meant it to operate. And obviously, again, it's all nice and good if you assume that two computers communicate by in the end, but sometimes the problem is that you know, there are network round trip times and stuff like that. Then the other problem is that you need to be able to persist such a global configuration or a global ground truth on individual computers that need to be able to restart out of this persistence in case of, let's say, whatever, power outage or just regular maintenance shutdowns and vice versa. And then another problem is, on top of that, is actually compaction. So the compaction meaning that there are a lot of messages coming into this configuration, like changes, whatever. We create a new collection consisting of 100 shards distributed over those and those 100 computers. All of that is applied to the configuration, but every individual command that actually manipulates that configuration doesn't need to be kept back to Stone Age, right? So you want to compact older states just really as a means to not rob every space, regardless of how big it is, on hard disks, on SSDs, and vice versa. Well, and then again, the consequences, which I will not just sum up here, but we will come to in a moment. Yeah. So this I pretty much have already said. There is one further point that I haven't mentioned so far, which is the last bullet, race conditions. Race conditions are obviously a very normal situation when a network of thousands of computers, even less, 3, 2, multiple threads, and so on, will face. Race conditions are generally conceptually trivially solved, but when you again have to make them work in a real environment, become really tricky. What we do with the consensus is we go a step further than just to keep a network-wide configuration. We do global monitoring of the ArangoDB database servers and coordinators using our own internal agency. And for other cases that people might come up with, and if you want to employ ArangoDB Agency for your own purposes, one of the key features would be obviously service discovery. That is very appealing. That would allow you, for example, to start the agents on a set of computers, and from there on, the next computers that join the network will just be communicated to the list of servers that are in the agency. And if you find a single one of them, that already is enough to discover the rest of the servers that are involved. Anyway, this all sounds like a simple problem, particularly considering that there are publications out there, but it really isn't. Okay, so the solution is consensus, and in the case of a software like ArangoDB, this is the animal brain of the cluster deployment. But you can think of other examples like distributed file systems or currency exchange systems. The etymological roots are in the verb Latin, and I put this one nice quote that I found on Wikipedia. The story around it is actually quite nice. You want to check it out. Right. When you think of consensus and you read on consensus in publications, you will see two different names out there. One is Paxos, the other one is Raft. Paxos was published beginning of the 90s, end of the 80s. This is a really old sorry. Okay. Yeah, here we are. So Paxos was published by Leslie Lamport, who's with Microsoft Research, I think now, in 1998. It's a very long paper. It's very hard to understand. It is fun to read. it really is fun to read. The reason why he called it Paxos is that he's contemplating the idea that there are some monks in a convent, and they have some sort of a democratic system, how they arrive at conclusions, and he tries to take that picture and apply it to a computer network with multiple services, and it's really fun to read. The paper that is way newer is from 3 years ago. It's been extremely successful, has been really an attempt to make consensus a lot simpler than it's done in Paxos. And Raft is, when you read it initially, maybe not completely easy to understand, but there is a vast difference between Paxos and Raft in terms of ease of implementation, as I find. First of all, ease of understanding, and then if you don't have the understanding, the implementation becomes obviously very, very hard. I gotta tell you though that still we somehow had the glorious idea of attempting to invent a simpler approach. And I can tell you, just don't do it unless you're really interested in the research and want to publish and have an idea of how to make everything simpler than it's done with Raft. Okay, so how does Raft work? For this explanation, I will actually switch to the browser and go on the web page of the developer of Raft. But key ideas is randomness in times that you wait for taking action. Actually, this is like, for me, the along with the majority rule, like the central key of how Raft operates fairly efficiently consensus store. Let's go to the, I have to stop this share, I think, or do I exit it like this? Yes. This is a visualization of Raft. I'm gonna go back all the way to the beginning, and then we start it over. There's in this case, 5 computers that are somehow connected to each other. The first thing that happens when you start life of a Raft cluster is that you reset local clocks to a random number between some upper and some lower limit. In ArangoDB, the default lower and upper limits are 1 second and 5 seconds. So anywhere between 1 and 5 seconds, you will reset your clock to and then start ticking it back. The moment that time is over, and you start in a state of a follower, that is that you're definitely not a leader and you're not candidating to become leader. Okay, the time is up on system number 5, and the first thing it does is it's gonna send out to all the others that he knows of a request for their vote. And having achieved that once, keeps repeating, keeping those nodes devout to its service. If S5 at some point, because it's cut off from the network or whatever, cannot send the vote requests quickly enough, at some point some other server will lose the patience and call for an election to become a leader, and a new server will become a leader when it has enough votes or to be more votes than the quorum, which is just a simple majority rule. A simple majority enough, so to say. That is that in that case, you know that they would not vote during the periods where the clocks are ticking backwards, and you are sure that for that period you're going to remain the leader of the outfit. In any case, anything that you take as an input that you're supposed to apply to the state machine and write to your logs will also only be approved, and you only respond to the client with a positive message once you know that a majority of the computers on the network have agreed that they have written down that rule, that they've applied it to the logs, and that's when you can go back to the client and tell it that yes, whatever A equals 12 was actually committed. Okay, so let's go back. There's tons to be said about Raft and all the tricky situations and so on, but I really encourage you to take the paper, have a look at this website, and read about it. It's not very complicated again, but it just needs some time, and it's a big paper. There are a lot of edge cases, and you want to go through all of them. Okay. Let me start the presentation again. Yeah, we talked about that. So again, the idea is random times quickly establish leadership, and once leader, keep your other members of the Raft consensus to follow you by constantly sending out notices of reaffirmment of your leadership. Then there are two problems: that you will lose that leadership if you don't get answers quickly enough. That means that in a situation where you're under high workload, these packages, if they cannot be sent out and received quickly enough over the network within the given limits, you eventually lose your leadership because somebody else will become impatient and start asking the remainders on the network to vote for it as a new leader. And you want to avoid that, obviously. If your Raft network is constantly preoccupied with re-elections, you cannot actually do any work, because without an established leader that has a quorum, a majority of the participants in the Raft network, you cannot operate. You cannot allow reads and writes to your state machine and to the replicator. The leader of the Raft network is the only point where you can have read or write access. Every other member will hopefully redirect you to the leader, because everybody knows at all times who the sole leader on the network is. And the leader is also in our case, in ArangoDB at least, the only instance where the key value store that is created by all these individual commands that are logged is kept. So every time a new leader takes over, they'll have to take the compacted state and apply anything since the compaction to create a new key value store, and that's the moment when it starts actually serving out, again, requests, writes and reads. Okay, the API is quite clear, actually. There is a read, there is a write, there is a combined read and write API, which we call transact. There is a possibility for you as developers or as users to have a look at the current configuration of the Raft outfit. This is all under the code directory ArangoDB/agency in our repository. The RESTful API is always in the case of config at rest with post requests. Okay, so what do they look like? This is syntax of the read, and I will for a moment leave the presentation so that I have the mouse so that I can show you the individual parts. Here we go. So the read API is addressed via posting an array of transactions. So the outside brackets are holding multiple transactions, while the inside brackets are, in this case, in the read API. I have a message here. I'm gonna get rid of it. Okay. In the read API, let me actually close this program before I get slacked again. Sorry for that. For the read API, the only things that you can send to the agency are strings of paths effectively to inside the key value store that you would like to access. There is one guarantee that we make, that is that anything that is within this outside brackets is applied in an atomic fashion. This applies to reads, this applies to writes, and what we mean by that is that there is guarantee that if you're asking for foo bars and the entire key value store through slash, that no other operation to the key value store, no other new log entry to the replicated log will happen in between. So the way this is meant to be used is that every collection of keys that you would like to get out of the agency that are put within the central, with the inner transactions, will be aggregated to one result. So if you ask for foo in this part, then you will get this bit as an answer, as a result for your initial, for the first key. This will be combined into one object with tree structure. If there is a certain depth to all these objects, then you will just get like one big JSON for, say, 10 different paths. They are going to be combined into one big document. And again, the last one is again delivered by itself, so it's kind of obsolete, right? I mean, the first result and the second result are both obviously included in the last, because this is giving you the entire key value store. The slashes up front are not mandatory. As you can see, in case of bas, this would give you /bas in this in the result. But if you want to get the entire agency, this is you really need to specify the slash. Also, something that is of interest, the combinations that go like this work such that if this was a part of foobar, so if you had, for example, foobar and foobar bas, then that bas would be included evidently within the, also maybe close my mail program. Okay. Are evidently aggregated, so that would disappear entirely under the foobar structure. Yeah. Again, this is transactional, and there will be no request made in between. So I'm just going to go over to a shell where we can just try a little bit the read API. I started a cluster on 3 of our machines in the machine room, C11, C12, and C13. This is the only difference between the machines, is, so to say, just the name of the machines, and I will have, as part of the talk, the configuration files that you may use for your own purposes to test this in the office or at home. And you would just have to slightly adopt to your own needs those configuration files to start a ArangoDB agency by yourself. Okay, so this is, again, let's look what's happening here. You already see the result up there. Let me clear this and actually call it again. Here we go. So this is a post. The L part is actually quite important. I will drop that in a moment, and then you will see what happens if I don't have the capital L here, which is actually follow redirects in curl. I'm getting the entire output of what is right now the key value store, and I'm asking computer C11 port 6660. This is an arbitrary port that was open and I just chose for this purpose. And then, yeah, the rest is just API agency read. And then I have a small JSON parser at the end so that we can actually see the results, not just manual within a line or so, and easier to read anyway. So let's see. The first thing that happened is this access to this computer actually led us to a new computer, and that's when we actually got the result back. So C11 is just forwarding us to the current leader. Let's see how we can see who the current leader is. I'm just going to delete all of this and say config. You can do that on any individual machine in the agency. And what you can see here is, let's have a brief look, is the term we are in. This, the term is the round of election where leadership was established in this case. When I started up the network of the three agents, they were able to establish a leadership within term one. There is no necessity for it to work that quickly, but it's very, very often the case that the randomness in the clocks automatically leads to a situation where the times are sufficiently far apart that network round trip times are way, way shorter in comparison, so that we immediately get to a leader within one election round. Leader ID is 856 whatever, which is an ID for a computer. These are unique IDs that are calculated at startup time and are supposed to identify an agent that, say, is restarted while the agency is still running. If it can come back and has an ID that is known to this agency, it will become just join in and start following the leader that's right now running the game, because 2 would be still enough. There's a majority of 3. The network would still function as a Raft store. Anyway, if this computer came back from whatever, a crash or from a network outage or for a power outage or whatever, and has still this ID, it will join the agency and get to catch up with whatever has happened since it's been gone, and while the agency was still working. So this is obviously what we're talking about when we talk about fault tolerance, that you have some tolerance for errors. Obviously, the Raft store cannot keep on operating if 2 out of 3 computers are not responsive. In that case, there is the majority of 2 just cannot be established, right? That makes perfect sense. That's obvious. Okay, so this is the pool of the agents. They're all active and participating in Raft store. This is your own personal ID of this computer. We asked C11, so C11's ID is down here, which accordingly also is depicted here in the pool. Then you see some other meta information like the size of the agency. You see your own endpoint in this case, and some other metadata like compaction step size and how many log entries you keep before where you make the compaction. So these are typical figures. If you just start the agency in ArangoDB Agency without specifying these parameters, these are the parameters that you are usually facing. They might change down the road in a couple of months when, if somebody's watching this video, they might have changed, obviously. But right now, as we are talking, in version 3.2, this is the situation. Okay, and then There is some supervision of the cluster going on now. That right now this is a standalone agency. There is no ArangoDB cluster to be monitored. That's why this figure doesn't really matter. But this these figures determine the way or the how quickly we respond upon, let's say, failures within ArangoDB cluster. DB servers that whose heartbeat has been, say, out for longer than this grace period of 10 seconds will somehow be dealt with. But before that time, we don't necessarily rush stuff. Okay, and then the next two things are, this is the version 6 of this configuration. This is just keeping track of things that have changed down the road. We started without, we did not start out of persistence, we just started with original command line parameters. Up here is also an important value. This is the current commit index. And this is just the number of log entries that we have so far logged in our agency. Now let's go back to the query. You see, I just practically, it seems, let's look, being just setting values for value A. And also, let me go back and remove the L here, as I promised, to show you what the effect of that would be. This is just pretty much a 307. And if you don't follow the redirect, yeah, it's just going to be an error. But if you follow redirects in your program, or if you use curl or whatever, libcurl, then you can obviously follow redirects. You would be directed to the current leader. Okay, let's me also show you this, that this is equivalent with this, and also equivalent with just dropping the slash. It all results to the same value. If I ask for a key that is not currently in there, you will see nothing. Let's get to the write API, which is not so far away from the read API. The difference in the case of the write API is that now we are somehow setting a value to a key. That's why now within the inner brackets, we have JSON objects. So for example, the first line up there is writing into the agency for value of a integer number 12. The write API is a little bit different in the sense that you may you may include more, and I have a typo in here. Terribly sorry. This is like the second revision, and I still have errors in here. Yeah, actually looking like this, the inner object brackets don't belong there. Okay, so a write request, the inner bracket consists of the assignment, which is going to be an object that somehow looks like this, a precondition, we will come to preconditions in a moment, and if you wish, a client ID. The client ID is meant to help out in situations when, say, you would like to track the result of a write operation at a later time. When would that be necessary? Just imagine you wanted to write the, some value to the key value store, and you are talking to the leader. The leader takes it, logs it into its replicated local log, not into the replicated log, in the local log, applies it to its state machine. Actually, the order is different, the other way around. Applies it to the state machine, writes it down in its local log, and then sends commands out to its followers to replicate that log. The leadership loses its leadership, but the followers have already gotten the write request. So your command has been actually applied, but the leader has passed away, crashed, network separated somehow. When you come back to the agency and would like to see, well, did it work what I wanted to write into the agency? you can take the client ID that is specified on your own site and inquire about your call here. And you would, from any other new leader, get either an answer with some indices, by that suggesting that your write was successful, or it would give you an empty list where you know, okay, so for this client ID, there is nothing in the replicated log. Okay, so what is the result of such a write request? It could look something, your write request could look like something like this. So set foo to true, set foo bar to true, and this is now a precondition, if foo's old value was false. So in this case, because this has been set to true and this is happening afterward, this command is not going to work. And then also specify a, let me see, so this is one bracket. This is the, yeah, so this would be exactly size write foo bar true, and under the condition that foo's old value was false. So this is the second bracket, so to say. You would first have this part applied, then this part applied. But again, don't forget, guaranteed that there is nothing going between foo is true and this next operation. And the last one saying, let me just put it in the next line so that's easily readable. The last part of your transaction says, assign the string baz to bar under no precondition, just do it. And this is the client ID under which I might come back and ask you at a later time, so what did you do to this write request? The client request ID could also be obviously whatever, Bart Simpson or so. But it does, I think that I don't have to advocate for that. Makes sense to have unique IDs that work here. Okay, so what is the result of the above? The result of the above could look something like this. This is an array where the individual members are according to the individual members up here. So the first here will be, this is a result of that. The 0 is a result of the center one, and the last one is the result of the last part of the request. Okay, what do we see here? This is either 0, which means that the precondition failed, and that's why foo bar true was not written to the agency, because we know that for sure, right? Foo's been set to true without precondition, so that definitely worked. But we can actually taste. I hope this is not going to break again. Let's just put this in the shell. Curl C11 16 API agency write post. Okay, so let's get started. Yeah, this would be the first part. The second part is this. And the last part would be this. And then we have two closing brackets at the end. And yeah, looks good. Okay, so this is without the L, no response. We want to follow redirects. And here we have this is the result that we got back. Let me do this again, just, okay, so this is pretty much what you were seeing in this picture, just with other indices, right? The first part worked because there was no precondition. The second part, the precondition was violated. That's why that was never written. And the last is this. Now, if I wanted to inquire using this client ID, by the way, again, because maybe somehow the connection got broken and I don't know if things went fine with this response. Aha, there we go. What have I done yet again? Is it like that? I have to go back and look. Ah, oh goodness. This is the wrong API. So let's go back here and write inquire, actually. As I said, inquire. And see what you get is, you see the index 688132. 13. Okay, I have to think about this a moment. Why is this? Yeah. Okay. Okay, it's easily explained. Remember, I invoked the command twice. I did it once without JQ so that you're not confused. I ran it once. Where is it? Ah, yeah, right. I ran it once here, and this is the result. I ran it again, and because I did not change the client ID for the second time, I actually get to see in both cases once the 688133 and once 688131. And yes, exactly, that's what I get to see. And you also see that it was applied in term 1 and what the query was. That bar is set to bus. Okay, and that happened twice. That's why we have these two different integers, the indices, the Raft indices that you get to see, 688131 and 688133. That's actually a nice example. Okay, let's go back and have a look at how the Write API has some equivalencies and what what kind of operations are available as of now. And we are going to put a lot more operations in there, but this is right now all that we need to operate the ArangoDB cluster. So if you have any urgent needs, just write us, write a feature request, and we will, if it makes sense, obviously we'll implement it. Okay, so let me, so that I have my mouse pointer back, exit the presentation, and oops, do it like this again. This is an assignment, A equals 12. Okay, fine, we know that. This is equivalent with that. So every time I'm writing something on the left, this is the effect that it has on the key value store. So starting with a clean sheet, if you applied, and don't forget that this is supposed to look like this, right? I'm just, for now, looking only at the inner transactions. A equals 12, this is equivalent to that. A equals 12, this is equivalent to that. It just uses this operator connotation. The next one is equivalent to that. There is an increment, there is a decrement operator, which will raise and lower integers. If there is not an integer before there, say if it's a string or if it's empty or if it's an array, in any case, anytime when it's not an integer, you will get to see 1 for increment. Decrement will give you evidently on an empty value or anything that's not an integer, -1 that I should mention. Also, you can increment with sprites. This can be very useful when you think of, and that's what we do a lot in, yet again, another program. And everybody's getting my nerves here right now, very good. So the increments can be very useful in big sprites because maybe you just want to block a pack of integers for, let's say, cluster-wide IDs that you want to make sure are absolutely unique. If everybody who would like to have, let's say, 10,000 IDs to operate on, doesn't for every individual operation come back to the agency, ask for a new integer, that's how you would do it. You would just increment the value and immediately after that read out the value that you got and then go back 10,000 and you would know, okay, this is the first index I can use and this is the last index that I can use. Push into a vector and prepend, put stuff up front or pop, shift, and vice versa operators. Okay. There is more API, this time with a precondition. So set A to 12 is A is equal to 12. With a clean sheet, this will not
be successful. Set A to 12 is if the old value of A is 12, this is equivalent to the above, it's also going to be 0. Say A to 12 if A is not empty, so old empty is false. Again, not the case. A is empty. And then finally set assign 12 to A if A's old value, if A's been empty. And this is the first time actually one of these commands is going to go through. And you will have a key value store where you have A is equal to 12. This is for your reference. You can check it out. There is a nice feature there that we built into the agency is that you may observe a value. For example, if you want to observe the key foobar, sorry, you can observe key, the key foobar, that's how you would observe it, and give us a URL that we call every time anything is changed to foobar or below it. That's this according way to get rid of such observation. What else do we have? The Inquire API I told you about. TTLs are a nice feature where you would like to set the value of A to 12, but only for 60 seconds. Then the value would be deleted. This is actually a very nice feature if you were thinking of system startup of hundreds of servers where you want to make sure that only one of them will make some initial configuration or so. Then you could come in and say, booting up or bootstrapping, for example, write a value for bootstrapping to true and who is right now doing the bootstrapping, or say bootstrapping and an ID of a server, and assign a TTL to it, so that in case that while you're bootstrapping, you as a server who's responsible for that bootstrapping crash, after 60 seconds, that value would disappear so that some new computer, some other computer gets a chance to bootstrap the service that consists of your many, many, many computers. That's one of the really nice and key features of ArangoDB as a Raft store, that you can assign those TTLs. This opens this vast field of opportunities where you can make things dependent upon stuff that are supposed to happen within a certain time, or else something else happens. Yeah, there is a transact API. The transact API this is all, by the way, documented obviously on our in the documentation online. So I'm not going to go in depth here, but this is a very nice thing where you can manipulate a value and immediately read it out, so that you know for sure that if you incremented the value of A by a number of 1, if you read out A immediately, that by that you know for sure what the value was before the increment. Yeah, I mean, this is an academic case, but there are a lot of situations where you profit from combined write and read transactions. And the result of such a transaction would consist maybe of a write up here, this is your write, and a readout of UID. The write would give you a Raft index of 171, for example, because the last index was 170, and give you the value of UID in the next part of the response. Okay, so how do you use the ArangoDB agency in real life? Well, you can use it again, as I just mentioned, as a one-time initialization to take care of race conditions in a big network, or think of configuration management. And as a matter of fact, that's exactly how we use ArangoDB agency. We have all the bullets that I put up here in a cluster, and that's how we use the agency to. So we start the agents first, and then tell all the other servers, the DB servers and the coordinators, where to find the agents. And once they're connected there, the rest just plays out by itself. We have a supervision that is inside the agency that is not really useful for anybody outside the ArangoDB context, that is outside the ArangoDB cluster. But what we did was we went a step further and not only have, so to say, a Raft store, but also a Raft program store, not only, so to say, key value store, but also a key program store, in which way we monitor DB servers and coordinators in a ArangoDB cluster. Let me give you some performance figures here. I plotted here a number of concurrent clients that are bombarding ArangoDB Agency with write requests in this case. And as you can see, when you grow the number of clients from 8 over 8, from 1 over 8 over 16, 32, and vice versa, you see that with growing number of clients, we can, because now you're becoming more and more efficient in terms of requesting a multi-threaded application like ArangoDB, keep on growing with the number of requests, and then we saturate somewhere in the limit of what we can put through the network and have the consensus agree and persist stuff to disk and so on. There's a lot of a multitude of factors that play contribute to these figures here. But what is really nice is that it scales very nicely with the number of clients. The number of clients that are bombarding the ArangoDB Raft network doesn't create big problems or so. The number, the curve never really declines again. And also I have some figures here for you, how putting a Raft network of ArangoDB agents of different sizes has an impact on how many requests you get through the system per second. So if you take a single ArangoDB instance that is supposed to deal with a key value store and persist stuff to disk, and you compare that with 3 agents, you're losing about, what, 1,800 requests per second in terms of performance. So these are the typical sizes of Raft networks, 3 or 5, because you start growing the network, you get a lot of network communication, and safety doesn't really, multiply. It's 3 or 5 computers are already a good, decent safety net, so that if 1 or 2 fail, you're still good. I mean, 2 fail for 5 is still fine. 1 failing for 3 is fine. But you see, these are figures that are, okay, half about the speed of that what a single agent would be able to do. But that's, I think, obvious that that somehow has an impact on performance. Okay, I've gone through my slides. I have some other slides here that are really meant for your purposes. I'm not going to go over those. I just want to mention a very nice package that Max Neuendorfer put online for how one could actually use the ArangoDB Agency in a small Go project, which demonstrates initialization management and also service discovery. Also, would like to mention that we are working on some stability and enhancement stuff in the version 3.2 following. They are not pushed yet to the development branch. They are part of a feature branch right now, and they enhance those figures that you just saw by about 30 to 40%. We did some good work there during the last 2 weeks or so, and also automatic agent failover will be part of that release, and for future we would like to allow for more assignment precondition operators. And with that, I would like to thank you for listening to this talk, and please do star us on GitHub if you like ArangoDB. There were a couple of questions so this is a re-recording because I did screw up the initial talk a little bit. I wasn't aware that I should read the questions. There were a couple of questions that I would like to address. One of them was if we could push actually one of these transactions online. I just put some of them into the command line, so that should be fine. Another question was how many concurrent read and writes per node. I think I showed that in the graph already. again, if number of clients grows, like thousands of computers on the network, there shouldn't be any really feelable burden on an agency. We're going to be doing just fine. And then, so it's a nice scaling system that has a bottleneck. The bottleneck is that you are doing Raft. You want to achieve a majority and you're pressing everything through one computer. Don't forget, the only way to talk to a Raft network is through its leader. So that's a bottleneck by itself. But this is the price that you're paying for fault tolerance and ultimate safety in this case. So what are the benefits of being able to use ArangoDB Agency's fault-tolerant persistent store? Well, again, I look at what Max Neunefer has written. Is a very, very nice and confined Go program, and you get some ideas of how this is a very, very nice and very useful thing to have if you're deploying a service that consists of X number of computers. What's the way forward to increase performance? I'm not seeing much right now. I don't think we can go so much better. We just actually did a gain of about, as I said, 30 to 40%, but I'm not sure if we can really do much better than that. But again, this is not a database, right? You're not just writing stuff in a collection. This is way more restricted, way more stronger guarded. There's a lot more guarantees that we're making that have obviously the cost. Again, thank you very much for listening. If there are any questions, just write me. You will find me on Twitter and on where else? You will find me obviously in the community Slack. Look for my name. Be happy to help. Okay, thank you very much, everybody. Bye-bye.